In this video, I'm going to show you the fundamental counting principle. Now, many problems in probability require the enumeration, which is the counting of the possible outcomes of an experiment. Where an experiment is any procedure to be carried out, such as flipping a coin or rolling a die. Now, all the possible outcomes of an experiment is called the sample space. And we can display the sample space, which is all the possible choices, using tables, a list, or tree diagrams, and then we can count the number of outcomes. So I'm going to show you an example here where we're going to use a tree diagram to list all of the possibilities. And then we're going to state how many there are. So let's say that we're going to flip a coin 3 times. So on our first flip, assuming that it's a fair coin, we will have heads or tails. So I'm going to draw 2 branches and label this as heads or tails. If the first coin is heads, and I flip a second coin, or the same coin even, I can get heads or tails. If the first coin was tails, I can still get heads or tails. So this first branch here is our first flip. This will be our second flip. And then we're going to flip one more time. And if I had heads and heads, in my third flip, I can still have heads or tails. If it was tails, I can still have heads or tails, and so on. So this last branch here, that represents my third flip. So to list my sample space, I can say that I have head, 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 which is the first branch here. Then I can have head, head, and then tail. And then I can have head, tail, head. And then head, tail, tail. Now with this tree, I'm guaranteed to get and list all my possibilities. So in total, we can see that there are 8 outcomes. All right, let's take a look at what the fundamental counting principle can do. So if a task is made up of stages, such as our coin flipping, where A is the number of choices for the first stage, B is the number of choices for the second stage, and C is the number of choices for the third stage, and so on, the total number of possibilities for the task is going to be A times B times C times ... So in our example above, we can see that there were 2 choices for our first flip. There were 2 choices for our second flip, either heads or tails. And there were 2 choices for our third flip, either heads or tails. So we can say that the 8 outcomes was based on the fact that it was 2 times 2 times 2, which is equal to 8. So let's take a look at some other examples. So let's say that a restaurant has 3 choices of salad, 5 choices of entrees, and 4 choices of desserts. How many different meals are possible? Now we're going to assume that we have to pick 1 salad, 1 entree, and 1 dessert. Or I'm going to say that we have to do this, even though I didn't write it in the question. So we have 3 choices of our salad. So we would say that we have 3, okay? And then we have 5 choices of our entrees. So if we think about the tree diagram, we would have salad, 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 3 choices. And then from 1 salad, 1 type, we would have 5 branches from just the 1 salad. So we're going to multiply that by 5. And then from each entree, we would branch off 4 choices for dessert. So we're going to go 3 times 5 and times 4, which then gives us 60 different meals. All right, I'm going to get you to try the other ones later on your own. Okay, so this brings us to something called factorial notation. So let's say that we have 3 people. how many ways can they be arranged in a line? And let's draw all the different possibilities. So let's call these three people A, B, C. So we can start with A, B, C. Then person B and C can swap. So we can have A and then C, B. Or we can lead off with person B and then A and then C. But then A and C can swap, so we have B, C, A. However, C can stand at the front of the line, so we have C, A, B. And then A and B can swap, so we have C, B, and A. So we can see that there are 6 possibilities. Now, using our fundamental counting principle from before, we can think that there are 3 places in our line, and the way to choose the first person, there are 3 possibilities. Now, once that person stands there, let's say we have A as Adam, B is Betty, and C is Chris. So there are 3 choices. Adam stands in the first spot. So now there's only 2 people left. So Betty and Chris. So there are only 2 spaces or 2 people left. So one of them stands there. And then there's only one more choice for the last person to stand in the last position. So 3 times 2 times 1 is equal to 6. So factorial notation is a notation that can be used to express a product of consecutive natural numbers in descending order. So that is an example here, 3 times 2 times 1. It starts from n and then it goes to 1. And we denote the factorial notation by n with an exclamation mark. So this is read as n factorial, not an excited n, but you can if you want. So n factorial, we start at n, and then we multiply that by n minus 1, and then we multiply that by n minus 2, and on and on and on until we get to 1. Now, one special note that we need to make is that 0 factorial is going to equal 1. Okay, and that's just saying that it's a special notation that you just have to kind of remember. So if I asked you what is 5 factorial, you can go 5 times 4 times 3 times 2 times 1, and that will be 120. Now you do have a factorial notation on your calculator, so see if you can find it, and you can also type that in. Now, what about if you weren't allowed to use a calculator and we did have to do something like this? So 6 factorial divided by 4 factorial. So we have 6 times 5 times 4 times 3 times 2 times 1 in the numerator, and then 4 times 3 times 2 times 1 in the denominator. So notice that these 4 numbers here cancel off with these 4 numbers here. So another way to write this is to say that we have 6 times 5, and then instead of writing 4, 3, 2, 1, we know that 4 times 3 times 2 times 1 is actually the same as 4 factorial. And then we have a 4 factorial in the denominator, which I don't have to write out because now I can see the 4 factorials in the numerator and the denominator. They cancel off. So now I only have 6 times 5, and I don't need a calculator for that, and I get 30. Now, I want to show you what to do when they're not numbers, but we have variables. So when we're writing our factorial and trying to simplify, you want to start with our largest number. So like in the example above here, 6 was bigger than 4, so we're going to start with 6 factorial, and then we're going to go 6 times 5 times 4 factorial, and we stop here because that matches with our 4 factorial in the in the denominator, which we can cancel off. So doing something similar here, we have n factorial, which is bigger than n minus 3 factorial. So we're going to start with our numerator. This will be n times n minus 1 times n minus 2 times n minus 3, and I'm going to stop here because that now matches my denominator of n minus 3 factorial. So these will cancel off. And then I'm going to be left with n times n minus 1 times n minus 2. Let's take a look at one more. So between n minus 4 and n minus 2 factorial, n minus 2 is actually bigger. So I'm going to leave my numerator as n minus 4 factorial, and I'm going to divide on the bottom, n minus 2. Now remember, we're getting smaller. So to get smaller means that we're going to go n minus 3, and then n minus 4. Notice I'm going to stop here because then again, now that matches my numerator. So the n minus 4 factorials will cancel off, and I have 1 in my numerator and n minus 2 times n minus 3 in my denominator. So now what I would like you to do is to try the other questions on your own and be prepared to share them with the class.